Okay, so in this chapter, we'll study motion in 2 and 3 dimensions. Okay, so the last chapter, we studied motion in 1 dimension, okay, and we were always interested in motion in 3 dimensions, and so we are going to study what we were really wanting to study, okay. So it's just extending the concepts we've learned um, last chapter. Okay, so here's a, so for instance, here's the trajectory of a satellite. What kind of motion is it? In how many dimensions is that? I'm sorry? That's a 2-dimensional motion, okay? So here, let me give you an example of a 3-dimensional motion. Okay, so this is where you are right now. So this is your helicopter, and let's say you're traveling like this. Okay, so here's your trajectory, and that's a 3-dimensional motion. Okay. We saw that, so what this is telling you, this is an earlier time, and those are later times. So this is T1, T2, T3, 3. So, okay. So this trajectory tells you where you were at all times. Okay. Now, what is the most useful way of describing this motion? What is the most useful way of describing this motion, which is a complete description of the motion? You give me this, your position as a function of time, that is a complete description. Okay? If it's a 3-dimensional motion, what I need is 3 coordinates. So if you're in Cartesian coordinates, I'll need your x coordinate as a function of time, your y coordinate as a function of time, and a z coordinate as a function of time. If it was 2-dimensional motion, all I would need is 2 functions. If it was a 1-dimensional motion, all I needed was 1 coordinate as a function of time. Okay? If it was an n-dimensional motion, I'll need n functions. That's all. It's as simple as that. Okay? So if you have your position as a function of time, okay, you have a complete description of the motion. Okay? What will we be interested in? Given your position as a function of time, there's a couple of things we are interested in. We want to calculate your velocity as a function of time, and we want to calculate your acceleration as a function of time. Okay? What is the velocity? Velocity is time derivative of your position as a function of time. Okay? So the time derivative of your x coordinate as a function of time gives you the x component of the velocity. Okay? What does the x component of the velocity mean? You take the component of the velocity vector in the x direction. Okay? This is the y component of the velocity, dy by dt. dz by dt is the z component of your velocity. Then you'll be interested in the acceleration. Okay, and it turns out that this instantaneous velocity, so if that was your trajectory, the instantaneous velocity is tangent to that trajectory. Okay, so here's your trajectory, and this guy is pointing in this direction. And of course, the magnitude of the velocity gives you your speed. Okay, so the speed tells you how fast you're going. Okay. Yeah. And all that information is contained in here. The magnitude and direction of the vector are contained in here. If you wanted to know your acceleration is time derivative of your velocity. Okay, so dv by dt, the time derivative of the x component of the velocity gives you the x component of the acceleration. Time derivative of the y component of the velocity gives you the y component of the acceleration. Time derivative of the z component gives you the z component of the acceleration. And what is this equal to? This is, of course, equal to d squared, the second time derivative of xt Okay, so given these three functions, which you did when in describing the motion, you were able to calculate the velocity and the acceleration. Okay, and those are the two things you're interested in. Okay. All right, so that's three-dimensional motion, and then we'll study some specialized two-dimensional motions. Okay, so that's what this chapter is about. You guys understand? All right. So what we want to do is, so let's say you get in your helicopter and you go on a flight. We want to describe that motion, and to describe that motion, what we need is your position as a function of time. Okay, and to give your position, you all have to use a reference coordinate system. Okay, so this is our reference coordinate system. This is our origin. Okay, here's our x-axis, y-axis, z-axis, and this is a right-handed coordinate system, and that's what we'll exclusively use. A right-handed coordinate system is when you turn if you turn a screw from the x to the y-axis, the z-axis points in the direction in which the screw would move. A right-handed screw would move. Okay, so if you turn from x to y, z points in the direction in which the screw would move. Okay. All right. So there's your location at this time. There's the projection of the location on the xy plane, and so here's the projection in the xy plane, and this is the x component, here's the y component, and here's the z component. Okay. So if you're describing a three-dimensional motion, you're giving me these three functions: x as a function of time, y as a function of time, z as a function of time. Okay. So let's say here is the trajectory. Now we'll define the displacement vector. Okay. All right. So if this was your location at an initial time, and with reference to the origin, there is the initial vector, position vector, and this was your location at a later time. Here's the position vector at the later time. Your displacement vector is pointing from the initial point to the final point. There's your displacement vector. The displacement vector is R2 minus R1. Okay. And the components of the displacement vector are x2 minus x1 and y2 minus y2, z2 minus z1. Okay. So again, if you get on your helicopter, take off for a flight, and come back and land to the same spot, what is your displacement vector? Zero vector. Okay. The average velocity is defined as the displacement divided by the time. Okay. So notice something. So if this was the displacement vector, for what is the average velocity going to be? It's going to point in the same direction as the displacement vector. That's a vector, and this is just a scalar. So this vector is going to point in the same direction as that. Okay. Its length would be different, and in this case the dimensions are different, but this vector is pointing in the same direction as that. Okay, so if you're calculating the average velocity, it will point in the same direction. The magnitude will depend on that. Okay. Again, like we said, average velocity really doesn't give you details of the motion. So for instance, if here's a different motion, and if along this motion you were here at once time t equal to 1 second, and you were there at time t equal to 3 seconds, and for this motion you were 1 second and 3 seconds. Here are two very different motions, and the average velocity is the same. Okay. Again, average quantities give you no details. Okay. So for instance, in this room, the average height is, let's say, 5'9", and you can totally change the distribution of people the type of people, and you can have the same average height. Bring in a bunch of NBA players and a bunch of midgets, you can have the same average height. Again, averages do not give you any details. Okay, so keep that in mind. Okay, you guys are all calculus experts, so what you're really interested in is instantaneous velocities. Yeah. So here's the average velocity, and in the limit delta t going to 0, this is dr by dt, and that's what you're interested in. Okay, what is your velocity at this instant when you're here? And dr by dt will be a vector, and this vector will be tangent to the trajectory. Okay. So dr by dt is your velocity vector. Okay. And so the x component of that is dx by dt, y component is dy by dt, z component is dz by dt. And that's the x component of the velocity, y component of the velocity, z component of the velocity. Okay. The magnitude of this velocity vector is your instantaneous speed. Okay. So the length of that vector is your speed. Again, no matter what your trajectory, the velocity vector is always tangent to the trajectory. We'll do an example in a second. Okay. Average acceleration. Again, when is it that you accelerate? When do you have acceleration?
Is it when your velocity changes?
When your velocity is changing, that's when you're accelerating. Okay. If your velocity does not change, you're not accelerating. Okay. So acceleration is defined as change in velocity divided by the time over which that change happened. Okay. So this is average acceleration. So for instance, if this was your trajectory, the blue line, and we just learned that the velocity is always tangent to the trajectory. Okay. So there's your initial velocity, there's your final velocity. And you can see that the velocity has changed. How has the velocity changed? What all has changed?
It decreased.
I'm sorry?
It decreased.
Okay, the direction of the vector has changed. Okay. And here it's not clear, but the magnitude could have changed as well. Okay. So velocity can change by its magnitude changing and or its direction changing. Okay. So let's say if you're driving on a straight stretch of road on 95, how can your velocity change? I'm sorry? No, you're confined to move on the straight stretch of 95. Can your velocity change? Hmm? Yeah, your magnitude can change. Okay, so then only the magnitude can change. Okay, so you see, when only the magnitude changes, the acceleration points in the direction of your trajectory. Okay, so you'll learn that, and we'll call that tangential acceleration, but we'll come to that in a bit. Okay, so for this example, both the magnitude and direction has changed. Okay, but okay, so here's that change in velocity that encapsulates all of that. Okay, so the acceleration is the change in velocity divided by time. Okay, in this diagram, they're showing you here's your change in velocity is final velocity. Change in any quantity is that quantity at the final time minus the initial time. Okay, so here was the initial velocity, and negative of that is that. So v final minus v initial is that. So here's the change in velocity. So which way is the acceleration going to point? In that direction. Okay, because acceleration is change in velocity divided by time. Okay, so the acceleration vector is going to point in that direction, and that will be something like that. Okay, so but this is average acceleration. Okay? Like I keep saying, you guys are all experts at calculus, so what you want is instantaneous acceleration. What is instantaneous acceleration? Here's the average acceleration in the limit delta t going to 0. That's the instantaneous acceleration. And that's dv by dt. All right, so let's notice something about this. So here's your trajectory. Okay? And the first thing you notice is the acceleration is not tangent to the path. Okay. So let me point out a couple of things. Okay. There'll be a component that is tangent to the path, and that is the acceleration that arises from this change in speed. And there will be a component that's perpendicular to the path, and that acceleration arises from the change in direction. Okay. So right now, you have an acceleration that is arising due to change in speed and change in direction. This is not exactly parallel tangent to the path, but that's how it should be drawn. Okay? All right, so your acceleration arises from change in speed, magnitude of the velocity, and change in direction of the velocity. Okay? Anyway, this includes both of those accelerations. Okay? So here's the acceleration due to change in velocity. So when I was talking about you driving on 95 on the straightaway, your direction couldn't change. This acceleration would be 0. You would only have that acceleration, which was tangent to the road. Okay? Did you guys understand that? Okay. All right, so your instantaneous acceleration is that. Here's the x component of the acceleration, y component of the acceleration, z component of the acceleration. Okay? And of course, this is equal to the second derivative of the position vector. Okay, so second derivative of the x coordinate, second derivative of the y coordinate, second derivative of the z coordinate. Okay? Let's do an example. Okay, so we saw equations. Let's. Okay. I want to describe a motion to you, and when I want to describe a motion to you, what I'm doing is I'm giving you there is the x coordinate as a function of time.
Is that 3t to the fourth or 3t to the seventh?
7. All right, so there's a motion, and that's described to you. All right, so if you wanted to calculate the velocity at any time, what you do is you take the time derivative of the position vector, and you help me out. Mm-hmm. 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 Okay, so the rule is the following. D by dt of ft gt, if you have a product of two functions, is f prime g plus f g prime. minus sine t. Okay? So derivative of t is 1, so cosine t minus t sine t. Do you understand that? Okay.
That's cosine t. Is that
Yeah, yeah.
that was cotangent? Is that not cotangent?
Cosine.
It's even worse.
All right. So the acceleration as a function of time is dv by dt. Hello there. You? Mm-hmm. No, you. No, the guy in front. All right. Go ahead. Are you going to help me out? Huh? No, not you. The guy. Mm.
E30t plus 14i.
Keep going.
Would be
126.
126t to the 5.
All right, you do the last part.
Negative sine t minus, I think it's cosine plus
Okay. All right, so here was an example where we had the position as a function of time. We were able to calculate the velocity as a function of time. We were able to calculate the acceleration as a function of time. Okay, here's the x component of the velocity. Here's the y component of the velocity. Here's the z component of the velocity. Here's the x component of the acceleration. Here's the y component of the acceleration. Here's the z component of the acceleration. Okay, so the force, again, you learn in a later chapter. If you want this acceleration in the x direction, this is the force you have to apply in that direction. Okay? You want this acceleration in the y direction, this is the force you would have to apply in the y direction. Okay? You want this acceleration in the z direction, you would apply a force in that direction. Okay? Now notice something about it. If you apply this force in the z direction and you don't apply any of these forces, these guys would be zero. So when you apply a force in a given direction, you change motion in only that direction. That's why we could treat the x, y, and z motion independently. Okay? All right. So now we've seen an example. Now we'll specialize, we'll consider some special kinds of motion. We'll consider a projectile motion. Here we'll toss a ball and we want to know the trajectory of the ball. And you guys all know that this is a parabolic trajectory. Under what conditions is that a parabolic trajectory? You will learn the condition under which this is a parabolic trajectory is when the acceleration is constant in this region, okay, and air resistance is negligible. Gravity is the only force acting on it, okay. So for instance, if you shoot a cannon that can go 40 miles up in the air, that won't be a parabolic trajectory, okay. So if a rocket is propelling it, then it won't be a parabolic trajectory. Only gravity needs to act on it. Okay? Gravity needs to be in the only force. So we'll show you that this is a parabolic trajectory. So we'll look at that motion, and here's another motion we'll look at. We'll look at circular motion at constant speed. Okay, so here are two-dimensional motions that we'll study, and these are important motions. Okay, so we'll look at that. Yep. All right, so projectile motion, air resistance is negligible. The horizontal and vertical motions are independent. Okay, so we'll draw our axis like that. The trajectory of a projectile is a parabola, and we'll show that to you. Okay. Let me show you a simulation. Okay, so that trajectory is parabolic. I want to see this. Okay. Okay, so you can see that the acceleration vector will be yellow, is the yellow vector, and the velocity components will see the x and y component will be the green vectors. Okay, which way is the acceleration vector going to be pointing? Downward. Okay, and it'll remain constant. When will it be constant? If you don't shoot it up too high. What is high? High is high compared to the radius of the Earth. Okay, so if you shoot it 50, 100 miles up, then acceleration won't be constant. But we don't have those kinds of toys. We can at best shoot it 20, 50 meters. Okay, so a will be constant. Okay, so let me fire the cannon. Okay, so you saw that it goes fairly fast. Okay, let's do a slow. All right, so notice that, look at the x component of the velocity. That guy doesn't change. Only the y component of the velocity is changing. Why is that?
Because the velocity forward is constant.
I'm sorry?
The velocity forward is constant. It doesn't slow down.
Yeah, I understand. Why is that? Is my question.
Acceleration is only pointed downwards.
That's right. The acceleration is pointing downwards, and it doesn't have an x component of the acceleration. To change velocity in any given direction, you need to have an acceleration in that direction. Okay, if you don't have acceleration in that direction, velocity will not change. Okay, and so that's what can be seen here. So in projectile motion, see the x component of the velocity remains constant. Okay, and it's only the y component of the velocity is changing, and it's changing in this direction because that was the direction of the y component of the velocity. Okay. All right. So I'm going to quickly show you that the trajectory is a parabola. Okay. From your calculus classes, you've learned that the equation of a parabola, a quadratic, the graph of a quadratic is a parabola. Okay. And if this constant is negative, the parabola is pointing downward, and so on. Okay? So what we'll do is, here's our setup. There's the x-axis, y-axis. This is your initial velocity. There's the x component of the velocity, initial x component of the velocity, y component of the velocity. Okay, so v naught is v naught cosine theta I plus v naught sine theta j. Okay. And what we are going to do is we are going to apply this formula to both the x and y component of the motion. Okay. So this is where we are starting. So this guy is 0. Okay. V naught x, this is the x component of the initial velocity. That is equal to that. And ax, the acceleration vector is that. The acceleration vector is 0I minus gj. Okay, it has no x component of the velocity, acceleration, and the y component of the acceleration is that. Okay, so if you put that information in here, what you get is x equal to v naught cosine theta t. Okay, and that is this guy. Okay, so I'm going to erase all of this. And now, oops, do the same thing for the y component of the motion. So y component of the motion is y minus y naught is v naught y t plus 1/2 a y t squared. Again, this is 0. Y is v naught y is v naught sine theta t plus ay is minus g, so minus 1/2 g t squared, which is that equation. Okay, so what is this giving you? It's giving you the x coordinate of this object as it flies in air. It's giving you the x coordinate. So what is the x coordinate right now? There's the x coordinate. What is the x coordinate right now? There's the x coordinate. What is the x coordinate right now? This is the x coordinate. And that is what this is giving you as a function of time. What is this guy giving you? It's giving you the y coordinate of the object as a function of time. And now what we'll do is, what is this equation telling you? So what I did was I solved for t here. T is x divided by that, and plug that in here. And so I got y in relation to x, y as a function of x. And now you can see that from here, y is a quadratic function of x, with the coefficient a being negative. So this is a parabolic trajectory opening downwards. Okay. So that's what we proved. Okay, where did the assumption that there's no air resistance go in? Acceleration was 0I minus gj. If there was air resistance, your acceleration would not be that. Your acceleration is that when only gravity is acting. Okay? And in addition, this was constant. Okay? So you can't throw objects 50 miles up in the air. G would not be constant. Okay? So that's where all those assumptions went. Okay, so what we have done is prove that the trajectory is parabolic. Okay, one of the things we'll be interested in is the range of a projectile. The range is the horizontal distance it travels when it's come back to the same vertical position. Okay. So you would be interested in this if you were shooting cannons at a ship and stuff like that. Yeah. All right, the range is your initial speed square times sine 2 theta. Theta is the launch angle divided by g. So you can see that for a given launch speed, if g were smaller, the range would be larger. Okay, so you shoot a cannon on Earth and you shoot a cannon on the moon, the cannon would go much further on the moon. G is about 6 times smaller on the moon, so it would go 6 times further on the moon. Yeah. So for instance, if Tiger Woods is playing golf on Earth and I'm playing golf on the moon, I can outdrive him. Yeah. All right, the other thing we are interested in, the maximum height the object travels. Yeah. The maximum height it rises, and that's equal to that. Okay. V naught square sine square theta naught, that's theta naught divided by 2g. Okay. Again, greater the acceleration due to gravity, smaller the height to which it rises. Yeah. Now, for a given launch speed, what is the maximum range you would get if you could change the launch angle? For what launch angle will you get the maximum range? You guys should know this. 45 degrees. That's because, see, the maximum value this guy can take is 1, and that is 1 for sine 90, meaning this would be 45 degrees. Okay? So that's where that formula tells you you get the maximum range for a launch angle of 45 degrees. Yep. Now, you also know from your trigonometry classes, sine theta is equal to sine 180 minus theta. Okay? So what does this mean? How does this show up? This fact shows up in the following fact. Okay. You see, the range is the same for complementary angles. And that's a result of this fact. Okay. The range for 15 degrees is the same as the range for 75 degrees. The range for 60 degrees is the same as the range for 30 degrees. Okay. So complementary angles give you the same range. Now, of course, real life throws a curveball at us. Okay. In real life, there's always air resistance and all that. Okay. So here's a trajectory. Here's a parabolic trajectory. Okay. But if the ball had spin, okay, this is where, so here's a ball with the top spin, and this is where it would fall with the same initial velocity. Here's a ball with the top spin. Okay. So if a ball has spin, what happens? Why did it fall like that?
Yeah, the acceleration exerting on the x-axis, so it's slowing down.
Okay, so this thing fell like that. Okay, so it fell faster. That means there must be a greater force than gravity acting in that direction. So the spin of the ball generated a force in this direction, in the downward direction, making it fall like that. Okay. Now, if you go on the moon and throw that same ball with the same spin, would that happen? No. The spin will not be able to catch any air, and the spin wouldn't affect the trajectory. Okay. And that's called the Magnus effect. Okay, so let's, I will... There's a video linked on the course website. I urge you to go see that. I want to finish this lecture, and I have only 13 minutes left, so let's go on to the next topic. Okay. So anyway, all I want to point out is, all right. All right, we'll go to that later. Okay, now we want to study another two-dimensional motion. Okay, so let's say you're driving in your car on a circular road and you're driving at constant speed. Okay, is your velocity changing? I'm sorry? I mean, you've covered both bases. There are only two bases. I got half yeses and half nos.
Velocity has to be changing.
Why?
Because it's,
The direction is changing. So here's a top view. There's the magnitude of the velocity is not changing, but the direction is changing. Okay? And we mentioned this. Anytime velocity changes, you're accelerating. Okay? So remember when we said earlier that when the magnitude changes, the acceleration is tangent to the path. And when only the direction changes, the acceleration is perpendicular to the path. Okay? And so if it's going in a circle, when it's perpendicular to the path, the acceleration is pointing toward the center. And so it's called centripetal acceleration as well. Okay? And now we'll give you the magnitude of, we'll derive the magnitude and direction of this acceleration. Okay? It turns out that the magnitude of this acceleration, the subscript C telling you it's a centripetal acceleration pointing toward the center of the circle, is the speed squared divided by the radius of the circle. And the fact that it's pointing towards the center is proved here in the next slide here. And I'm just going to point you to the proof. Okay? So here's a car. Here you are driving in a circle. Okay. At this instant, there's your velocity. Okay. So there's your x-axis. Your location, angular location is theta. And this angle will work out to be theta. There's your x component of the velocity. That is equal to v. So at this instant, the velocity vector is your speed sine theta, the negative sign telling you in that direction, plus v, the y component is cosine theta, j. Okay. And from this part, sine theta is yp, your y coordinate divided by r. So the velocity at that instant is minus v y divided by r I plus cosine theta is x divided by r. So when you are here, there's your velocity. Okay. What we are trying to do is show you that the magnitude of the acceleration is that, and that the acceleration is pointing toward the center. Okay. So there's the velocity. Okay. So you're going at constant speed in a circular motion. R is not changing. V, the magnitude of the velocity is not changing. So this guy is not changing. That guy is not changing. The only thing that are changing are the y coordinate and the x coordinate. So if you take the time derivative of that, that will give you the acceleration. The time derivative of that is that. The time derivative of x is that. Okay. So there's the x and y component of the acceleration. And so you can rewrite them in that. And if you calculate the magnitude, you get for the magnitude v squared by r. Your speed squared divided by r. That's the centripetal acceleration. Okay. And if you calculate the angle, so there's the acceleration vector, and there's the x component of the acceleration, there's the y component of the acceleration. If you calculate this angle phi, tan phi is that, and which is equal to tan theta. Okay, so phi is equal to theta. Yeah. So the acceleration vector is pointing toward the center. So that's what this slide shows you. And you can go read it a little more carefully. Okay. All right, so again, let me summarize what we're saying. Okay. So if you are driving in a circle at constant speed, the magnitude of your velocity is not changing. What is changing is the direction. And when only the direction changes, the acceleration is perpendicular to the trajectory. When the magnitude changes, your acceleration is parallel to the trajectory. Okay. So this acceleration is called the centripetal acceleration, hence that subscript c. Yeah. So when you're driving on a curved road, what does this show you? It has a tangential acceleration. What does that mean? That means your speed is changing. Okay. And here's the centripetal acceleration. It's also called radial acceleration. That's because the direction of your velocity is changing. Remember, the velocity is always tangent to the path. Okay. When you're on a straightaway, your direction is not changing. So if your speed is changing, all you'll have is tangential acceleration. When you're going around the curve like that, your speed is still changing, and since the direction is also changing, there is a radial acceleration. Okay. So again, tangential acceleration, radial acceleration. Okay. So tangential acceleration arises due to change in magnitude of the velocity, change in speed, and radial acceleration due to the change in direction of the velocity. Okay. Again, when is it that you're accelerating? You're accelerating as long as your velocity is changing. If dv by dt is not zero, you're accelerating. And velocity can change by its magnitude changing or its direction changing. Okay. So tangential acceleration is when magnitude changes, and radial acceleration is when direction changes. All right. The next thing we want to study is the following. It's related to the following fact. Let's say this is a lab. And this is a train. That is moving at a constant velocity relative to this lab. What does constant velocity mean?
No acceleration.
No acceleration. Its magnitude is not changing and the direction is not changing. You can go in any direction you want, but your velocity is constant. Okay? And now we'll say that you've done a whole bunch of physics experiments here, and your buddy's done a whole bunch of physics experiments there. Okay? Hundreds of years, it doesn't matter. Okay? If the two frames are moving relative to each other at constant velocity, these are known as inertial frames of reference. What you will find is what the laws of physics you find and the laws of physics your buddy finds will be identical. Okay? So in inertial frames of references, the laws of physics are identical. Okay? And we won't show all of that. So what we'll show is the following. So we'll show the simple fact, this simple fact. So here's an example. So here's your buddy, pushing a cart in this. He's applying a force here, giving this guy an acceleration A. And you're watching this from here, and what you see is this, you also see the same force and same acceleration. Okay? So your buddy says the motion of this guy is force equal to mass times acceleration, and you are also going to see a force equal to mass times acceleration. You're seeing the same thing. Okay. All right, that's what I'm going to quickly show you. Okay. So here's your frame of reference. Here's your buddy's frame of reference in the train moving. Okay. And so your buddy's location is changing with time. Okay, so the notation is as follows. This is frame A, this is frame B. That's the location of frame B with respect to A. That's the notation. Okay. Here's a particle. So here's a particle on which the force is being applied. Here's the position of the particle with reference to frame A. The position of the particle with reference to frame B. Okay? And here's the velocity of frame B with respect to frame A. Okay, you can see that RPA, this vector, is equal to this vector plus that vector. That's what RPA is, RPB plus RBA. RBA plus RPB. Okay, so now you have an equation. And again, when you have an equation, you can hit this guy with a hammer and you hit this guy with the same hammer. You take the time derivative of that. You take the time derivative of that plus that. This is VBA. See, that's the rate of change of that, which is the velocity with which the frame is moving. Okay. And this is the velocity of the particle as observed by this frame, and this is the velocity of the particle as observed by this frame. So here's another equation. We'll use the hammer again. Time derivative, okay. This is the acceleration of the particle observed in this frame. That is the acceleration of the particle observed in this frame. And this was 0 because remember, this guy was moving with a constant velocity. So both frames are observing the same acceleration. Okay. What we have shown is in this train that your buddy was doing experiment, he observed this acceleration. You standing on the side of the road observed the same acceleration. That's what we showed. And you're seeing the same forces being applied. Okay? All right. Here's one more thing that we'll need to see. We'll talk about, okay. So we will need to transform velocities. So let's say you're driving on a rainy day. Okay. The rain is falling straight down with respect to the ground. The question is, what do you see? Okay, right. So the rain falls straight down, and what you see is this velocity. Okay, and the way you come about that is the following. Okay, so this is, now we'll give this a new notation: velocity of the rain with respect to ground, velocity of car with respect to ground. Okay. And the velocity of the ground with respect to car is negative of velocity of car with respect to ground. Okay. Velocity of the car with respect to the ground is to the right. Velocity of the ground with respect to the car is the ground is moving backwards, which is that. Okay. So here's how you add velocity. Velocity of rain with respect to the car. Here's how you read the notation. You can always add another letter there. Is equal to velocity of rain with respect to ground plus velocity of ground with respect to car. Yep. And so this is equal to velocity of rain with respect to ground minus velocity of car with respect to ground. Okay. And that's what this is showing you. Okay. So this is equal to that, which is velocity of rain with respect to ground with velocity of car with the ground with respect to car. Okay. And that's the velocity of the rain you see in the car. Okay, so we will need to use that in problems. Okay. And that's what we'll do next time. Okay.